Everyone say hi to your parents. Nobody wants to say hi to your parents? I'm so sad.
Oh, is our voice being recorded?
Yeah, everything's recorded. Okay. So we are going to start with, because this unit is called the inverse, okay, of sine, cosine, and tangent in 7.1. Let's review what the inverse functions are supposed to be. When you have the regular function, which is f of x, and you're going to compose, right? Composition is different from multiplication. So this is a composition. So an inverse function, it's now the input, I'm sorry, not inverse, no, regular function, f of x is composed with f inverse. It has to equal to x, okay, for every single x in the domain. And that means it's not an or, it's an and, both has to be true. F inverse is composed with f, it has to also be x for all x, again, in the domain of inverse. If that's true, okay, if the composition of f inverse and f and both come out to be x, then f of x and f inverse are inverses of each other, or the two functions are inverses of each other. The inverse function, the domain and range, what's happening to the domain and range of the two inverse functions? They're just switching, okay? So the domain of the regular is now the range of the inverse, and then the range of the inverse is now the domain of the regular, okay? So you can switch them. Now when we graph it out, the regular function, which is f, and its inverse, so this notation right here, f to the negative 1 power, is now an inverse of that, are symmetric with respect to the line y equals x, okay? So if I fold it diagonally, they should line up on one on top of one another. If a function y equals f of x, which is a regular function, if it has an inverse, okay, then the equation of the inverse, all we're doing, can you see these two? We're just switching what? X and y for x. And a lot of times in lower math classes, we don't like x equals. So guess what we normally write it as? Y equals, so we solve for y, okay? So that's what we do. So we switch them, but then we always solve for y. All right, we are going to try to do sine, cosine, and tangent. Here we go. Complete this on your own. Well, let's do one together, because I don't know. Sine graph, I'm going to need 5 points. What's the period, by the way, for sine? 2 pi. So I'm going to start 0 all the way to 2 pi. So x and y. 0. Sine at 0 is 0. Sine at pi over 2 is? Sine at pi? 0. 3 pi over 2? And last one? Yep. Okay. I'm going to make 2 pi to the right. I'll do 2 full cycles, one to the left and one to the right. My formatting is a bit off. Is your formatting a bit off, or you guys are fine? Nope, a bit off. I made too much on the top. So 1 and negative 1. And do you guys remember that we divide the period out into how many equal parts? 4. So that's a pi. This is a 3 pi over 2. So each tick mark is worth a pi over 2. And let's plot the dots. Here we go. 0, 0. Pi over 2 is 1. Pi is back at 0. 3 pi over 2, negative 1, and 2 pi is now 0. Okay, and round out your max and min, because if you have some pointy looking thing, it's going to mean something completely different later in calculus, okay? So that's one period to the right. And we are just going to continue to the left. So repeat the pattern. Down, 0, up, and 0. Okay, so there you go. So look at the graph. Is this graph 1 to 1? What is 1 to 1? Who remembers?
If you do a horizontal line and a vertical line, it only intercepts the graph once.
All right. Okay. 1 to 1 means every input can only have one output. Every output can only have one input. That means it has to pass the horizontal line test. In this case, does it?
No.
No. If I draw a horizontal line, doesn't it intersect like infinitely many times, depending on how long I go? Yeah. So this one does not pass. So guess what? This is not a 1-on-1. because your answer is no, okay, we have to restrict its domain. And here's why we restrict it. Here's my sine graph. If I were to go and do its inverse, or graph its inverse, would you agree that I'm just going to switch x for y and y for x? So its inverse is just going to go, something like this, right? Is that even a function? No. So that's why we have to restrict its domain so it can be a function. Okay, so its inverse can be a function.
If you were to do it like what the thing you highlighted, why is that considered not a function?
Oh yeah, how come this is not a function? Yeah, because you know why? When I pick one x value, I have infinitely many different y values, and that's not a function.
But you can have infinitely many
y values. Right, so for example,
like the actual sine graph.
So this sine graph is actually a function, but it's not a one-to-one function. Okay, so I'm gonna pick. Let's make this like, there's no Julia in here. So this mark, we're gonna call her Julia. Okay, this mark, we're gonna call her Cindy. Okay, this mark, we're gonna call her Ashley. There's no Ashley in here. Okay, we're gonna call her over here like Rebecca, Katy Perry, Rebecca. Okay. So what's happening is, let's pretend the Y is like the boyfriends. Okay. Okay. So this line, we're gonna say there's no John. Okay. Right. So can you see that like John is dating what? 2 girls. Oh yeah. So if I was to write an order pair, so Julia, comma, John, right? And Rebecca, comma, John. I know. But it's funny. It's functional. John can be a cheater. John can be a cheater and it's functional. It's like the man's world, Okay. But the moment that we have, guess what? The moment that we have what? Girl cheating. Oh, that's looked down upon. So that's not functional somehow. So when you have a boy cheating, somehow whoever created math said it's okay.
And it works. The X is like 2 X chromosomes, and the Y is a Y chromosome.
But we're gonna make it like one-to-one functionable world. So one boyfriend can have one girlfriend or one partner, We're not gonna be cheaters in here. Okay? No cheaters in trig. So that's why the trig itself, it's function, but it's not a one-to-one function. So that's why we limit it. So guess what? They all one-to-one. Okay? So we have to restrict its domain. Okay, so it can be a one-to-one function. Can you put a one-to-one, a 1-1 function? A one-to-one function. So put 1-1 in front of it. Okay, so here we go. Universally, you guys are all mathematicians in here. You're going to come together. We're going to decide to cut off a part of the trig function. So it can be a 1-to-1. So where would you cut off? Okay. Where would you cut off its domain? I mean, where do you want x to start and where do you want it to end so it still be a 1-to-1?
Negative pi over 2 to pi over 2.
Okay, how about you guys? We're going to take a vote. 0 to 2 pi?
Yeah.
Okay, what do you want? What he said? And then you guys have, what did you guys say over here? I forgot. Negative what?
Oh, I did negative pi over 2 to pi.
Okay, so I got the yellow domain and the pink domain. It's the yellow domain 1-to-1?
No.
No, because I'm cutting through twice.
Oh.
So eliminated.
0 to 1.
0 to what? Change your mind. 0 to what?
No.
No?
Not mine.
Never mind.
See, I said Amy.
So it's Amy, here's my question. Can I extend Amy's answer a bit further? Like, can I go negative pi over 2 to like here? No, because then guess what? This little thing right here makes it a non 1-to-1. So Amy said, you know, I'm just going to stop at pi over 2. Okay. Technically, though, let me ask you this. If another team said, you know what, I don't feel like using that. Can I go here to here? Would that be okay?
Yeah.
Yeah, right? It's still 1-to-1, but universally, we have to agree. Not because one's better than another, but probably we have to kind of come up with the same answer for students, right? So which one's easier? The pink interval or the yellow interval? Why pink easier? It's in the center. A little bit of positive, a little bit negative. There's a zero value that's always easy to calculate. So that's why universally they came up and said, you know what? I'm going to limit this from inclusive, negative pi over 2, all the way to positive pi over 2.
But doesn't the graph keep continuing on to like 2, 3 pi over 2?
Oh yeah, it goes. That's why I have arrows. Like, the graph itself.
Yeah, I know, but why would the domain be restricted then just between those two?
Because remember, our goal is the reason we have to restrict it. So this piece and only this piece can be what? I'm only interested. Can be a what? A 1-to-1. Okay, because it's a 1-to-1. When I turn it sideways, is a function now. Okay, let's graph that out. Let's copy and paste. Let me define this, and I'll copy that pink part down below. Inverse of a sine, remember, all we do is switch x and y. So it used to be y equals sine of x. Now we switch x equals sine of y. But we don't like x equals. So we go in and solve for y. Well, when we solve for y, it's already an inverse. And to make it known that it's an inverse, we use f to the negative 1 power of x. So this is f inverse of x, which is now sine inverse of what? X. Okay. Let's state the domain and range of sine inverse. What is the domain of sine inverse? So the domain, the range of sine inverse, and I'm going to put it back to quadrants, back to the unit circle, okay? Okay, so the domain. What's the domain of sine inverse? Yeah, because I can look at the range of the regular. Would you guys agree? So the range of the regular was from negative 1 to 1, okay? Now, what's the range of its inverse? Keep in mind, we chopped it off for a reason. Lucian?
Negative pi over 2, pi over 2.
Right. We chopped it off because we can't use all real numbers, right? We cut it off from here to here. That used to be the chopped off domain. So now is the range of the inverse. So inclusive, whoops, negative pi over 2 to pi over 2. Did you guys remember this at all in Algebra 2 Trig when you studied it? Did you understand why we had these restrictions back then? No? Do we know now why? Yeah? Let's put that back to the unit circle. Oftentimes, I'm going to say, well, what quadrants is sine inverse restricted to? What would you say? What quadrants? What is it? What? 1 and what else?
3.
Not 3. Remember, it's from negative pi over 2 to pi. Isn't this right here negative pi over 2? What quadrant is that? 4. And then pi over 2 is here, right? So guess what? It's 1 and 4. Okay. 1 and 4. So now, is it clicking why we're using quads 1 and 4 sine inverse? Because of the restriction, negative pi over 2 all the way to positive pi over 2. So now let's graph out that cutoff piece. Okay. All right. Here we're going to graph out the cutoff piece. The cutoff piece was only from negative pi over 2 all the way to pi over 2. So when I switch them, that's the max I'm going to go. And there's a 1 somewhere. So half of that is pi over 4, but I don't need pi over 4 for sine. 1, where would I put the tick mark for 1? How far out? A third of a distance, 2/3 of the distance, About how much out? Pi over 3 is about what in decimals? About 1.1.5, right? Because pi is about 3.14. Can we agree? Divide by 2. Yes, no, maybe? So it's like 1.5-ish. So if I were to make a tick mark for 1, can I go like 2/3 of its distance? Would that be okay to do? Okay. All right. First dot. I'm going to use the first dot. This dot right here. Can you see that? That is negative pi over 2 comma what? Negative 1. So negative pi over 2 comma negative 1. Make a dot right there. Okay. And then 0, 0. Then positive pi over 2, it's what? Positive 1. Can you see the curvature of my original, the pink curve? It's kind of hugging the x-axis a little bit. Okay, so we're going to hug the x-axis. Right there. So class, this is y equals sine of x. Restricted. I'm going to pause right there before I go and graph out its inverse. That's sine of x restricted. What points are we using for inverse? Okay, what's my first point? Give me the first point.
Negative.
Okay, negative 1, negative pi over 2. I'm going to use a different color. Negative 1, negative pi over 2. Beautiful. So negative 1, negative pi over 2. And 0, 0 is obvious, right? Last point. 1, yep, pi over 2. So here we go. 1 comma pi over 2. This is the inverse. I got 3 dots. Should I make a straight line? No. How are we curving this? So it's hugging what? The y-axis. Whoa. Okay. Now, if I were you, I'd probably try to draw in this line. What line am I drawing? That's right. Let me just cut through. Y equals x. And obviously I'm freestyling. So does it look like it's about symmetrical? Okay. Obviously when you graph things by hand, it's not like exact. Decimal would do a better job. But so that's what an inverse and its regular look like. Hold on tight so you can ask me questions. All right, you guys go ahead and start on cosine. Graph out y equals cosine of x and answer the box. I'll give you 2 minutes to graph and answer the box. And we'll define the inverse of cosine together. 2 minutes. I'm probably right there in the folder.
It's not
Dollar, right? Because it means dollar. Yeah. So that is dollar. So this is what you made in class? Okay, that's 2 minutes. You guys done? No?
Always two.
Can you compare your cosine graph with your team? Make sure you guys are on the same page. If your team has like pointy tops, tell them to round it out. Okay, so here we go. Just give me the 5 points, okay? Lauren, cosine of 0 is?
1.
Good. Cosine pi over 2? Cosine of pi? Very good. 3 pi over 2? And back to 2 pi? Perfect. Okay, so round out the top and bottom, y'all. Okay, and repeat. Here we go. 0, -1, 0, back up at 1. So again, is this a one-to-one class? No, because you said no. We have to restrict its domain so it can be a what? It's a one-to-one function, okay? Okay, why don't you in your group agree or disagree or argue over where you want to chop off? That's what we use. I'm Asian. This is how I shuffle. Huh?
If you're doing that, you're just reversing the order.
Yeah, so let's see. So now this top guy is now in the middle somewhere, right? This top guy is in the middle somewhere.
So you're just reversing the order.
Yes and no. I am reversing the order, but they're not like.
Like the bottom few cards are always going to be closer to the top guys every
Because like this 5 guys can go here, right? But then there's not exactly like on, like not every card is flipping. Yeah, you're right. It is a little bit. Okay, restriction. Alex team, what did you guys fight on? What do you guys want to cut? What do you want to cut off?
0 to pi.
0 to pi. Alex says 0 to pi. Okay. Yeah? Any other? That's it? Everyone agree? Man, you guys are no debate, nothing. Okay, 0 to pi. C. Okay. Inclusive 0 to pi. Okay. So inverse of cosine, we normally again just switch x for y and y for x. Okay. But most of your books like to have y equals, so we do that. We go in, hey, y equals. Because it's an inverse function now, we use f to the -1 power of x, which is inverse function. So now we go in and compose cosine inverse of x. Next, we are going to state the domain of cosine inverse. We will also state the range of cosine inverse. Then we are going to connect it back to the unit circle, which is the quadrants. Okay. Domain of cosine inverse. What do you guys think? -1 to 1. Okay, because the range of the original was -1 to 1. Now, what's the range of cosine inverse? 0 to pi, wherever you chopped it off at. Quadrants. Let's connect this back to the unit circle. 1 all the way to 2, because 0, pi is right here. So cosine inverse, we can only use quads 1 and 2. Okay. Now, because we use 0 to pi, here's pi, Then I need to make a 1 tick mark. So 1, so 1 about 1/3 of the way, 2/3 of the way, 1/3 of the way, because pi is about 3. Okay, so this is 1, 1, negative 1's over here, and negative 1's down here. All right, let's plot the dots. Okay, at 0, we had our original at pi. At pi over 2, I need to make a mark for pi over 2, don't I? Pi over 2 is right here. Pi over 2, staying at 0. And then at pi, can I go down to 1? I'm sorry, negative 1. So it's right here. Oh, I went too far, sorry. 0, it's like that. I went too far. 0, it's at 1. Okay. And then pi over 2 is at 0. And pi is negative 1. So this is like that. So this is y equals cosine of x with restriction in domain, okay? Now let's graph its inverse. Give me point number 1. What is the first point that you can use to plot its inverse? 1, 0, right there. Point number 2. Okay, 0 pi over 2, so here's pi over 2 is right here. So 0 pi over 2, right there. Point number 3. Negative 1 pi, all the way up there. Straight line? No. Hugging the y-axis, okay. Okay. Now, and again, if you like to, you can probably draw in this line called y equals x to see if you are somewhat near symmetrical. If and whenever you guys miss your dot, just make your dots really fat. That's why all my dots are super fat. Okay. I want to make sure I don't miss the point. Okay, last graph, and I'll let you go. Tangents. Go ahead and start. Should I give you 2 minutes like last time or 3?
You scroll up
Down or up?
to see the cosine.
Like that?
Yes.
Okay. Mm-hmm. So 3 minutes? What's the period for tangent? Pi. So you just go right pi, left pi. What's tangent pi over 4? 1. Tangent pi over 4 is 1. What is tangent at pi over 2? 1 to be fine. That's what asymptotes going to go. Guys, remember we graphed this on your parent function. All right, Ryan, give me your 5 points, bud. Oh. Oh. Okay, Ryan.
Negative pi over 4, negative 1.
Negative 1,
0, 0, pi 4, 1.
Mm-hmm.
And then
What happened at pi over 2?
undefined.
Okay.
So it's just a vertical asymptote. And then 3 pi over 4 is negative 1 and pi 0.
Perfect. So put in another asymptote over here. Make sure you guys, this is a nice straight up and down curve. Okay. Please don't do this. Okay. We can't have a lot of ups and downs. It's nice and straight. There's no min, there's no max, can't have humps and bumps. Okay. So if you really want to, you can go another one over here. It's really up to you. Similarly, you can always do more than 2 periods, but usually that's sort of the demand, 2 full cycles. Okay, 1 to 1?
Yes.
It is?
Oh, no. Darn. Heck no.
Isn't it like, I intersected like 3 times, just like that. So, 1 to 1? No. It's a trick question. Okay, so we say no. We limit it so it can be a 1-to-1 function. Okay. Okay, so decide. Where would you chop it off?
Negative pi over 2 to pi over 2.
Okay, that looks like a nice curve, right? Yeah. Continuous. Okay. But for this case, we do not include the endpoint, so we're going to go parentheses, negative pi over 2 to positive pi over 2. Okay. Inverse of tangent. Just like the other 2 functions, we are just going to switch x for y and y for x. Okay. Then we go and solve for y, which now it becomes an inverse. So now we're going to go tangent inverse of x. So these 2 are exactly the same, just kind of written differently. So domain, range, and connect that to quadrants. What's our domain? Oops. What's our domain for tangent inverse? Perfect. Negative infinity to positive infinity. Okay. If you want to write all reals, I'll take them all. Range. Right. Negative pi over 2, non-inclusive, all the way to pi over 2. Let's connect that to the quadrants on your unit circle. What quadrants is tangent inverse in? 1 for sure, because that's positive pi over 2. What else? 0? 3? Where's negative pi over 2 at?
Oh, it's a negative pi over 2.
Right here, right? Don't we go clockwise? So 1 and what? 4. 1 and 4. Just a hint. None of the inverse functions are ever in quad 3. Okay, let's graph out our regular restriction, which was simply from negative pi over 2 to positive pi over 2. And positive pi over 2, negative pi over 2. And there's a half, which is pi over 4. Okay. And again, I need to make a 1 tick mark. So can I make a 1 tick mark 2/3 of pi over 2? Yeah, so somewhere here is 1. Okay, so that's 1. This is 1. This is negative 1. And this is negative 1. I'm going to start with the asymptote because I can graph that. Asymptotes, asymptotes. And again, just like what we did here, we're just going to copy the top curve over. Pi over 4 is 1, negative pi over 4 is negative 1, 1 continuous. If you have to invade other spots, feel free to do so. You missed your dot, just make it fat. There you go. So that's our regular tangent with restriction. Now we're going to obtain 3 points to graph the inverse, and we'll call it a day. What's my first point? 0, 0. I love that 0, 0. What's my next point? 1 comma what? Pi over 4. So 1 comma pi over 4. Last point? Negative 1, negative pi over 4. So negative 1, negative pi over 4, somewhere over here. All right. Hugging, which axis? X, okay. Should I put the asymptotes in there so I know I'm going to go towards it? Yep, asymptotes are cool because it tells you where to approach. Okay. And if you need to turn your paper sideways, do so. I tend to do that because I don't draw a very nice curve. Does it look like it may be reflecting over this line if we were to kind of have somewhat of a decent graph? Yeah? All right, that's our day.